All right, this lecture is about overfitting. We've learned about how to train a neural network and how to build neural networks and train them on data sets. Now I'd like to talk a little bit about what we're actually trying to achieve when we're solving this optimization problem. So in this lecture, we're going to talk about overfitting. Develop a process. The goal is to develop a process to use our labeled data to generate models that can predict the future unseen samples. So it's not about learning to give the output for samples you've already seen before. The goal here is to train a neural network so that when you give it samples or data it's never seen, produce a reasonable output. Okay, so let me give you an example of that. Suppose you have a data set of drug dosage versus your blood sugar. So maybe it's insulin or whatever, and it's reporting some deviation from some normal level of blood sugar, up or down a little bit. So I've got some data here, and you can see the dose is on the horizontal and the blood sugar is vertical. And we've collected 6 data points here. So your doctor would like to use those 6 data points to predict what your blood sugar would be if she gave you a different dose. Okay, so the data set has 6 samples, and since this is a regression problem, the input is anywhere from -1 to 1 in this case, and the blood sugar will also be some value. So we're looking for a fitting curve. We're modeling a function. So there's a continuous domain input and a continuous domain output. In these sorts of problems, we want to use linear activation in conjunction, so linear activation function on the output in conjunction with the mean squared error loss function. Okay, so your doctor takes that data and creates this neural network with one input node, because that's just it's only the dose as input, and 2 hidden layers, and each hidden layer has 250 ReLU nodes. That's rectified linear units, and then 1 output node for the blood sugar. And she trains it on your data set for 2,000 epochs, goes through those 6 points 2,000 times. And here's the loss. Actually, this is the log of the loss over the training epochs. And you can see the loss does go down really nicely. It goes down by orders of magnitude. And by the end of it, the loss is 1.57 times 10 to the minus 10, a teeny tiny loss. Great. So that's a big success. So your doctor wants to give you a dose of 0.65, and she uses the neural network that she just trained to estimate what your blood sugar will be. And so the model says your blood sugar will be 1.0043. So on this plot over here, at 0.65, which is over here somewhere, it's just above 1. So the new point is right here. So I don't know about you, but I'm not sure that's such a great model. I can see how it's close to a previous point, but it maybe is a little bit too close, because this data is suggesting some relationship between dose and blood sugar, but those points aren't like gospel truth. Those points are a bit noisy, like what different metabolic things are happening. Metabolic is a big word, but sometimes I like to use big words that I don't understand because it makes me sound more photosynthesis. So we don't necessarily want to fit all those points specifically. What we do want to model is the underlying phenomenon. So in this week's exercises, they'll show you that the neural network model looks very much like the linear interpolator of these points. So if the neural network, when you push through a whole range of points, doses between -1 and 1, you see that the model looks a lot like this. Now, That's great for fitting those points, but we don't really want to fit the points. We want to fit the underlying phenomenon. Those points have noise in them. So suppose a doctor takes 300 more blood samples from you at a variety of different doses. And once you're drained of blood, she runs the data set through her model to see what the mean squared error loss is again. This time, the loss is 0.018. So that's not even close to the original training error that we had. Remember, the training loss was 1.5 times 10 to the minus 10. So this is tiny by comparison. So the false sense of success we get from our training data set and training on our training data set is known as overfitting or overtraining. Okay, we get really low loss, but that doesn't necessarily, that only shows how well we fit our training data. It doesn't necessarily tell us how well it's going to work on data we haven't seen before. So in particular, if your model, if your neural network has enough flexibility in terms of numbers of parameters that you can adjust, maybe how many neurons there are in the hidden layers, how many hidden layers there are, whether or not you're including a bias, all these sorts of things. If your model has enough flexibility and you train it long enough for enough epochs, it will start to fit the specific points in the data set, in your training data set, rather than fitting the underlying phenomenon. That produce the noisy data. Okay, starting to fit the noise of the training data set. That's essentially what we were doing up here. We're fitting these specific training points and not the underlying phenomenon. Recall that our sole purpose was to create a model to predict the output for samples it hasn't seen before. How can we tell if we are overfitting or overtraining? A common practice is to keep some of your data as test data, which your model does not train on. So you remove some data, that's going to be your test data, and all the rest of your data you use for training. So you put some of your data aside as test data, which will not be seen during training. Does not train on. Then as you're training, you can compare the loss on your training data versus the loss on your test data. So here I'm showing something from the notebook, showing how the training data goes down. Again, this is a log scale, so it's going way down. It's orders of magnitude lower than the test data, which is up here. In fact, if you look closely, you can see the test data goes down, but then it starts to kind of creep up again. Why? That's because the model is working so hard to fit the training data, it's starting to fit the noise of the training data at the expense of the test, at the expense of fitting the test data. So it's like putting these extra wobbles in here to fit these these training points, and sort of ignoring, well, it doesn't know about the test points in behind, so it's but it is becoming a worse model of the test data. Okay, so divergence like this is a sign of overfitting. So it's especially when your test loss starts to increase as your training loss goes down. Joke break. A bartender says, "We don't serve time travelers here." A time traveler walks into a bar. Okay, let me describe to you a another method that's used to assess when we have too many degrees of freedom for a particular learning scenario, and we're prone to overfitting. Or basically, it's another way to see if you're overfitting. Validation. So if you want to estimate how well our model will generalize to samples it hasn't trained on, we can withhold part of the training set and try our model on that validation set. So the test set is at the very end, our sort of final evaluation. But as we're going, we want to be able to have some feedback of whether or not we're overfitting. How many epochs should we train? How many layers should we have? How many nodes per layer? What's the learning rate that we should use? All these parameters need to be tuned as we go before we try our data on the final test and have some final indication of how good a job we've done. So validation set is another subset of your data that you set aside, and you can try your model on that between training sessions. Once our model does reasonably well on the validation set, then we have more confidence that it will perform reasonably well on the test set. Okay, so it's common to use a random subset of the training set as a validation set. So let me populate this, this graphic here. So when you're, this big box on the outside here is our neural network model. Now, inside our model, we have a set of hyperparameters. This is stuff like I just said, number of nodes per layer, number of hidden layers, learning rate, all these sorts of things. Now, in that context, we also have parameters, things that we're going to adjust for our optimization process, the learning process itself. These are connection weights and biases. Okay. So what we're doing is we take our training set and we update our connection weights and biases. So this is update using training set. And so we repeat this process, updating using our training set over multiple epochs. So we train it for a number of epochs with a particular set of hyperparameters, and in order to see if we've overtrained it, we can evaluate our model, our trained model, on a validation set. So this is something that we, like a feedback loop that we operate on as an outer loop of our learning loop. Our learning loop is run over many epochs, and once we're done learning, we can check on the validation set. Once we've done that a number of times, then we feel like we've, after every validation, we can adjust the hyperparameters and say, oh, we are overfitting there. Maybe our training loss was really low, but our validation loss was much higher. We've overtrained it. We fit the noise, not the underlying phenomenon. So then there are certain things you can do to your hyperparameters, which I'll talk about in the next video, to accommodate or fight against overfitting. Once we've done our validations and gone through this process a number of times, and our validation loss and our training loss are the same order of magnitude, then we're confident, then we can be confident that once we expose our model to data it's never seen before, not in the training set or the validation set, it should still perform fairly well. And that is the testing phase. Evaluate using test set. And I'll put a bigger arrow for this because It's something you kind of do just once at the very end. So these are the sorts of processes you add into your neural learning procedure in order to at least detect if you are overtraining or overfitting. Next video, we're going to talk about some specific mechanisms you can build into the neural network itself that will guard against or combat overtraining.